Hi everybody, welcome to our lecture today. We are going to talk about mixing different languages together, from the shell scripting that we've been doing to C programs and to some Python as well. So the bash shell script, the language that we use to make that work, is not the only standard Unix scripting language. Another one that is also encountered on all Unix systems is awk, A-W-K. And we can mix all these things together with the programs that we write ourselves. Awk was originally invented by these three gentlemen, Alfred O., Peter Weinberger, and Brian Kernighan, the same one that helped write the C programming language. And it is commonly used for writing one-line programs that need to be integrated into other systems. We see a lot of awk in the early days of Unix because the ability to do math on the command line didn't exist in the early versions of the shells. Nowadays with bash we have these operators, the $, double parentheses, that we can just do arithmetic directly in. But before those were added to the shells, awk was kind of the only way to do this easily and simply. You still find a lot of examples for awk online, so it's nice to be able to know how it works and what it does, or at least to get a little example of it. So here's a simple little example for awk. You can see that it uses the same sort of hi, I'm a shell script, here's my interpreter to use for this particular script. And here is a simple print statement. We have some kind of old school begin statements here that almost look like basic, but this thing will print out hello world. And awk has a really interesting feature called an associative array. In a normal array, what we're doing is we're mapping numbers out to some object. So whatever you pick, maybe the number 6 maps to the string Jones, and maybe the index 2 maps to Nahasapima. So we have different things that we can all have as targets for whatever the index into the array is. But an associative array will map an arbitrary object to another arbitrary object. So maybe we have the string Nahasapima, maybe that maps to Apu. And maybe eat more beef is a string that happens to map in the array to kick less cats. So we might even have something with arbitrary objects where you pass in some reference to myObject1 and it maps to an integer 6, or myObject2 maps to 7. So kind of the inverse of the way we traditionally look at an array with integer indexes. So we could even mix them up. So an awk associative array might have things like where the number 0 maps to the string dog, and maybe the string cat maps to a string feline, and maybe the number 3 maps to the number 6. So we call this a sparse array. And sparse arrays mean that there are holes in between the different entries. It doesn't just go contiguously from 0 to 1, 2, 3. We've got things in between. So we'll call that a sparse array. These sparse arrays, or these associative arrays, you may also have heard them described as maps or hashes or lookup tables. It's all about the same thing. A way to take an arbitrary entry and map it to something else. So another language that you'll see very commonly used in Unix is Perl. And Perl is also a general purpose programming language, and it was a Larry Wall invention from the late 80s. It stands for Practical Extraction and Report Language. And it borrows from everything. So he wrote this to solve a lot of text parsing problems, just to try to make a little more full-featured language in the day. So you'll see stuff from SED and Lisp and awk and all kinds of different stuff in there, and certainly heavy C usage. It's supposed to be easy to use, but it's not very elegant. It was this one guy who is an amazing guy, but he was the only person working on this language. So we might have a sample like this. So the top line is the same thing for a script interpreted language. We define where the interpreter is. We can talk about how strict we're going to be with various arguments and usage of the language. We can describe whether or not we want to see warnings printed, and then we can just print directly to the system, or to the system out. One of the classic books that we see, one of the O'Reilly published books, is the Perl Camel. So the camel is kind of the symbol, has become the symbol for the Perl language, and a lot of that's because of O'Reilly. We'll see those pictures get used to help define lots of different languages out there. This particular code is an interesting bit. This uses the Perl header again to show that it's that kind of script. It says camel code, and then has all of this text in here to do this. If you actually execute it, it produces a bunch of camels, which is kind of neat. And you can grab the source code from here. But Perl lets you do this kind of text manipulation and management in a really nice way. So on the other hand, Python is an additional language that we also see in Unix. It has similar philosophies, but Python has really overtaken the world compared to Perl. Perl is great, but Python is an active development, and it's an active usage by lots of different people. It's a faster language, has really good support for actual object-oriented programming. It's well linked into other languages, and it's being taught at lots of universities, whereas Perl really isn't at this point. So both of these are what are called interpreted languages. When you want to run the code that you've written, what happens is that the interpreter loads up your code, and sometimes it'll do some slight optimization, which they might call compiling, but it's really not compiling. And then it just executes the script line by line by line. Each line has to be passed to the underlying user interface, or the underlying shell, and executed from there, and the results returned back to the interpreter. So Perl can only be interpreted by Perl itself, the program Perl. Python is interpreted by Python. And similarly, Java programs can only be interpreted by the Java executables. So an example script for Python might be, here's the same define statement that says to use the Python interpreter, and just print hello world. We can easily open files with a very C-like syntax, and then write out to that file. So very simple file and data or text manipulation here. We can run an example script like this, so we cat out our script. We can see that it's simply the print hello world, give it a executable permission so we can run it, and then run it. So just very, very like bash scripting. If we want to build up a string in Python, this is much easier to do than it is in bash. So we can take a string and define it equal to some actual sequence of characters, and then we can use the plus equals assignment operator to concatenate strings together, which is a lot easier than using the cat program or even stringcat in C. So we can then add other things to it and then print the whole thing out. And we can have functions in the midst of this long concatenation that's happening. This particular one converts the number into a string, the number 9 into a string. So otherwise it would be an integer, so we have some much better typing, at least in terms of these functions. Note that we did not define the type up here. We see the same kind of thing even in more modern languages like JavaScript. So JavaScript, you also don't define the type out in front of the variables. Here is another example. This one's called Python Math, and this is specific to Python 3, one of the newer versions of the language. Python 2 is still used an awful lot, but one disadvantage with Python is that Python 2 and Python 3 are quite dissimilar. They're not compatible, and that has really segmented the user base, which is a little unfortunate, but the Python 3 stuff is much better, so if you're going to start working on one, I'd say learn Python 3, but it is a warning sign that the language seems to be mutable. Alright, so catting out our particular program here, we can see the Python interpreter is being called for, and we define two variables and then a third variable. We just use them. We don't have to put these in a subshell or anything like that. The variables actually get added together into 13. That's handy. And then we can print things out. Here's kind of a printf-like functionality. We can put 0 into these curly braces, and with the dot format, then we can take the 13 integer and convert it into a string with a string function and get formatted printing back into there. And the output is 6 plus 7. How much is 13? So handy stuff. The difference between an interpreted language and a language that has been compiled as an actual machine code on the operating system cannot be overstated. So let's take a look at this. This particular program, called c-billion.c, counts from 0 up to a billion, and every time it iterates, it takes I and multiplies it times itself. So we have a billion multiplies as it counts its way up to a billion. So here's the compilation of it, and then we're going to run it. And before I just type in the name cbillion, I'm going to actually run another program here. This is user bin time, and then I give it a format here which will tell me how long this particular program takes. And the way the time program works is that you pass it the name of another program that you want to time. And when you hit enter, it will run that program and return the time to you. So here we can see that cbillion took 2.78 seconds to run. So a billion multiplies on a multi-user server that's busy doing other things took 2.78 seconds. Conversely, the Python version of it, here's the Python version of counting to a billion, multiplying each time. When we run the same time program against Python billion, we see that it takes 160 seconds. So they're not even in the same league. Multiple orders of operations slower to interpret the language than it is to just run a raw executable. So the point here is that it allows us to combine the best parts of one language with the other. So we can take the speed of C and the ease of programming of Python and combine them together. We can take our compiled languages, the executables we get from them, and combine them with scripting languages. So mixing C into Python is fairly easy. So here we've got a Python script. We've got, first of all, a C program called cbillion, and then in our Python script, Python billion fast, our Python script starts up and it does an import and it calls cbillion. So when we then run our Python script, and here's the time entry that is running our Python billion fast script, this then calls the C program, cbillion, and it tells us that the Python script took only 2.91 seconds. So pretty good. We were able to run a lot faster just because we had C do the math instead of Python. So getting the data back into Python is a little bit tricky though. In our previous one here, this doesn't return any results back to Python. This is just Python running a program and letting the program do what it's going to do. But to get data back into Python is a little tricky. So one way would be to write a C program and then have it access a data file, which is then read by Python. That would certainly be one way to share data. We could create a Unix pipe, which we're going to talk about in an upcoming lecture, and then Python and C can both read and write from that pipe. We could also create a C function inside Python with there's a third-party module called Instant that you can add that lets you just write C directly inside Python. And then some of the more classic ways involve, there's an API for Python and C together, and there's all kinds of different stuff from C types and Swig and the Boost Python API, and all of these use some additional wrappers or APIs to manipulate the data back and forth between the two programming languages. So certainly options, but they're not really trivial. By the end of this course, you should be able to do the top two. So creating a Unix pipe and writing a C program that simply writes to a data file that Python can read. Those should be fairly easy for you to do. So we can write a program that calls Python and then returns the value back to C. So our C program calls Python, gets the data back. So why would we want to do that if C is the fast language? The reason would be because string manipulation can be so painful in C that for managing that and opening up files and writing to them, maybe we just want to do that in Python instead and then get the value back into C. And there's an official long example here for some of the original Python docs, and you can look at the different versions to figure out which one we are. This one could be from 2.65, this particular documentation, but you can find all kinds of different stuff in terms of finding how to call Python to get the value back into C using the online documentation. So let's mix some C into our bash shell scripts here. So the first thing we'll do here is we'll cat out the contents of our .c file, which is called add6-c. And here's the contents. And what this thing does is it takes a character argument. So it takes a bit of text that's entered in, and then it immediately converts it to an integer. So you can see that atoi is the function that we use to convert entered text from the user into an actual integer representation in C, adds 6 to it, and then printfs it out. Now printf sends its data to standard out. So what this function does is it takes an integer that is typed in by the user, adds 6 to it, and sends it to standard out. The return value is what's given as the exit value of the program once it's run. Compile it, make sure that works just fine, and it does. And now we're going to look at a shell script in Bash that we've written. This line says it's a Bash script. Then we set a variable called value equal to 4, and then we print that out to verify that it does in fact have the value 4. Then we're going to set that same variable equal to the output of this subshell, and this subshell is going to run the add6-c program that we have above with itself as the argument. And it could be any precompiled binary. It doesn't necessarily have to be the one we've done, but you could put any binary in here that you could access from the shell. It could even be a shell script, as long as it outputs something interesting here. Then we printf the output, and what this is going to do is it's going to grab the new value that is read from this variable that's been set inside value and enters it into the string that we're reporting to the user. Give it a executable permission here with the change mode command, and then run it. And we can see that the value starts at 4, and then because of the add 6 is equal to 10. And that should do it for this particular script. Now, if we instead change this particular line and we add quotes around it, like it says here on this red callout box, if we add quotes around this, then we get an interesting error here. And the error is that the command add6-c space 4 could not be found. And the reason for that is because when you surround something in quotes, it's evaluated as one argument. So this subshell that tries to run tries to take this entire thing as one argument and find a program that matches that and then run it. But program names don't have spaces, so of course it can't find anything, and this line fails, and then it prints out the same value again. So be careful. Sometimes quotes are not what you want, and this is one of those cases. All right, well, I hope that was instructive for you about learning about mixing various languages together, and we will see you online. Thanks again.